In this video, we will discuss what matrices are. We will discuss the definition of matrices, the order of matrices, and the two types of matrices, which are the square and rectangular matrices. First, let's discuss the definition of matrices. Matrices are a rectangular array of numbers that are enclosed by a pair of brackets. Now, let's discuss some examples. Let's take an example of one element, which is 2 here, and it is enclosed by a pair of brackets. So we will say that this is a matrix. In this next example, we have 2 entries or elements, you can call it whichever you like, and it is a matrix as well, as it fulfills both requirements. In the same way, we have this next example. We will call this a matrix as well, as it is fulfilling both requirements. It is a rectangular array of numbers and it is enclosed by a pair of brackets. Now in this next example, in which we have all elements present except for one. Since an element is missing, this will no longer be a rectangular array of numbers, as you can see. It is enclosed by a pair of brackets, but it is not fulfilling one of the requirements, hence it is not a matrix. In this next example, we will see what rows and columns are in a matrix. These horizontal lines are denoted by M, and these are called rows. Over here we have 3 rows. In the same way, these vertical lines are denoted by N, and these are called columns. In this example, we have 3 columns. Hopefully by now you will have some clarity of what rows and columns are. Now let's see what the order of a matrix is and how to find it. The number of rows and the number of columns in a matrix is the order of a matrix. M by N is a way to write the order of a matrix. Let's explain this with an example. In this example, we will first see how many rows are in this matrix. As you can see, we have 3 rows here. And then we will see how many columns we have, and in this case, that is also 3. So we will say that the order of this matrix is 3 by 3. 3 by 3. Now we will discuss the types of matrices. Now there are many types of matrices, but over here we will only discuss rectangular and square matrices. Now always remember that rectangular and square matrices are opposites of each other. Like, let's take a look at the rectangular matrix. In the rectangular matrix, the number of rows and the number of columns are not equal. In other words, M is not equal to N. Let's take a look at an example. Over here we have 2 entries enclosed by a pair of brackets. We will see how many rows and columns we have. There is only one horizontal line, so we only have 1 row. And there are 2 vertical lines, so we have 2 columns. Since 1 is not equal to 2, M is not equal to N, so we will say that this is a rectangular matrix. In this next example, we have 3 rows and 1 column. 3 is not equal to 1, so this is a rectangular matrix as well. Now let's look at the square matrix. In a square matrix, the number of rows and columns are equal, which is why it is the opposite of a rectangular matrix, as mentioned earlier. An example of this is a single element, as it has 1 row and 1 column. 1 is equal to 1, hence it fulfills the condition of m is equal to n. So we will call this a square matrix. In this next example, we have 3 rows and 3 columns. 3 is equal to 3, so we will call this a square matrix. Hopefully this lecture helped. Types of matrices. So we'll be discussing row matrices, column matrices, diagonal matrices, scalar matrices, and identity matrices. So what are row matrices and column matrices? So simply, a row matrix is a matrix that has one single row. It can have more than one column. We're not really concerned with that. It must just have one row for it to be a row matrix. An example of a row matrix would be this matrix here. It has one row, but it has 2 columns. And we're not concerned with the number of columns. It has one row, and that's all it really needs for it to be a row matrix. And let's say this matrix here. It has one row and it has 4 columns. We're not concerned with the number of columns. It has one row and hence it is a row matrix. And the order of a row matrix is basically a 1 by n matrix. So basically one row and n columns. A column matrix is simply the opposite of a row matrix. It must have one column, and that's all it really needs. It can have more than one rows. We're not concerned with that. And we just need one column. An example of a column matrix would be this matrix here. It has 2 rows and it has one column. Again, we're not concerned with the number of rows. It has one column, and that's all it really needs for it to be a column matrix. The order of a column matrix is basically an m by 1 matrix. So basically m number of rows and one column. Now, what is a diagonal matrix? Now, a diagonal matrix has 2 requirements. One, it must be a square matrix, so basically an m cross m matrix. M number of rows and m number of columns. They must be equal. And the second requirement is that the elements outside of the principal diagonal must be 0. So let's see what that means. You see this matrix here. The elements inside this rectangle make up the principal diagonal. Every element outside of the principal diagonal is 0, and hence this is a diagonal matrix. Now, an example of a 2 by 2 diagonal matrix would be something like this. These 2 elements, they make up the principal diagonal. The elements outside the principal diagonal are both 0, so this is a diagonal matrix. This is a 3 by 3 diagonal matrix. These elements make up the principal diagonal. Every element outside of the principal diagonal is, that's right, 0. So this is also a diagonal matrix. See this matrix here. These elements make up the principal diagonal. Now, even though the principal diagonal itself has a 0 in it, we're not really concerned with that. The principal diagonal can have whatever elements it wants. It can have zeros, non-zeros, non-digits even. But every element outside of the principal diagonal must be 0. And hence this is also a it is also a diagonal matrix. Now, what is a scalar matrix? A scalar matrix is basically a type of diagonal matrix, so that is the first requirement. It is a diagonal matrix, and every element inside of the principal diagonal, so the diagonal elements, must be equal or same. So this something like this here. This is the principal diagonal. Every element outside the principal diagonal is 0, so this is a diagonal matrix for 1. And the elements inside the principal diagonal are both equal to A. So this is a scalar matrix. See this here. the elements outside the principal diagonal are both 0, and the elements inside the principal diagonal are equal, and they're equal to 2. So this is also a scalar matrix. Over here, the elements inside the principal diagonal are equal to 5, and every element outside the principal diagonal is 0. So this is also a scalar matrix. Now, an identity matrix is a type of scalar matrix in which the diagonal elements are equal to 1. So a 2 by 2 identity matrix will look something like this. See, these elements, they make up the principal diagonal. The elements outside the principal diagonal are 0. The elements inside the principal diagonal are both equal, and they're equal to 1. So this is an identity matrix. This is a 3 by 3 identity matrix. Every element outside the principal diagonal is 0, so it is a diagonal matrix for 1. Every element inside the principal diagonal is equal. So this is a scalar matrix as well, and they're equal to 1. So this is an identity matrix. Null or zero matrices. So basically, any square or rectangular matrix in which all the elements are 0 is called a null or zero matrix. That's about it really. It is denoted by this big O, and here are some examples. See this matrix here? It is a 1 by 1 square matrix, and the only element in it is 0. So this is a null or zero matrix. This matrix here, it is a 2 by 2 square matrix. All the elements are 0. So it is also a null or zero matrix. This matrix here, it is a 2 by 3 rectangular matrix. It has 2 rows and 3 columns. And every element in this rectangular matrix is 0. So it is also a null or zero matrix. And that's about it really. Now what are equal matrices? For two matrices to be equal, there are two conditions. They must be of the same order, so the number of rows and columns of both matrices must be equal, and their corresponding entries must also be equal. So what this means is, see, let's have two matrices A and B. What this represents is the element of A in the ith row and jth column. Similarly here, the element of B in the same ith row and jth column. So basically the element of A in the and B and the element of A and B in the exact same positions in both matrices. So if they are both, if every corresponding element of A and B is equal, then the matrices A and B are also equal. What this really means is, let's take matrix A here as 1, 2. Let's take matrix B as 1, 2. So by just looking at them, you can tell that A and B are both equal. But to justify this explanation we made, this element of A is the element in the first row and first column of A, and this is in the first row and first column of B. They are both equal, so we've ticked that one. And the second element of A, 2, is in the first row, second column of A, and the second element of B here is in the first row and second column of B. They are both also equal, so we have also ticked that, and hence A is equal to B. That's about it really. So I and J can both be any real numbers. Let me just remember that A and B must be of the same order, and the corresponding entries must be equal for A and B to be equal matrices. So Another example, just to clarify, is let's just say we have matrix A here. It is 1, 2, 3, and 4. Matrix B, 1, 2, 3, and 4. They are both of the order 2 by 2, and their corresponding entries are equal: 1 and 1, 2 and 2, 3 and 3, 4 and 4. So A is equal to B. Now, the addition of matrices, if we have matrices A, second, if we have matrices A and B, and they both are of the order m by n, so they have the same order, they have the same number of rows and the same number of columns, then we can add them up, as in A plus B. So the order of A must be equal to the order of B. And that is the only requirement we have to add A and B. So let's just see a small example of this. If we have matrix A here as this, and if matrix B is this, and we want to find A plus B. Now, the order of A is 1 by 2, 1 row, 2 columns, and the order of B is also 1 by 2. So they can be added up. And how do we add up A and B? Well, we'll add up the corresponding entries. The first element of A will be added to the first element of B. So 1 plus 3. And the second element of A will be added to the second element of B. So 2 plus 4, which will give you 4 and 6. That will be the result. Now remember that the order of the resultant matrix will be the same as the order of A and B. So just remember, you have to add up the corresponding entries. Now see this example here. We have to add A and B. We have to find A plus B. Now first, we must make sure that they have the same order. A is of the order 2 by 2. B is also of the order 2 by 2. So indeed, they can be added up. Now, we have to find the sum by adding the corresponding entries. So, see here. The corresponding entry of 1 here is 2. The corresponding entry of 5 is 0. And as you can see in the resultant matrix, it's 1 plus 2 and 5 plus 0, 4 plus 5, and 3 plus 6. And this is the resultant matrix. Now see the subtraction of matrices. It is similar to how we have done the addition of matrices. It also has the same requirement. A and B both must be of the same order, m by n. So the order of A is equal to the order of B. And in this case, we'll just subtract the corresponding entries instead of adding them. So if we have, say, matrix A as similarly as we did before, 1, 2, and B is 3, 4. If we have to do B minus A, well, you'll simply just write it like 3, 4 minus 1, 2. And the resultant matrix will be subtracting the corresponding entries. So 3 minus 1 and 4 minus 2. And this will be a result. Now see this example here. We have to subtract a and b, a minus b. So let's first see the order of a is 2 by 2, 2 rows and 2 columns. And the order of b is also 2 by 2. So they can be subtracted from one another. So a minus b, well, as we've seen before, we'll subtract the corresponding entries. So 1 minus 1, 6 minus 2, 5 minus 9, and 5 minus 3. And this will be your resultant matrix. Now, what is the transpose of a matrix? Well, the transpose of a matrix is found by changing rows into columns and columns into rows. So let's see what we'll deal with. So this is how you would denote the transpose of a matrix A. So let's just say we have matrix A here, like this. And we have to find A, we have to find A transpose. So what we'll do here is we'll change the rows of A into columns. So the first row of A will become the first column of A transpose. The second row of A will become the second column of A transpose. And if you look at it the other way of converting columns into rows, that has also happened automatically because the first column of A has become the first row of A transpose, and the second column of A has become the second row of A transpose. Now see this example here. We have matrix A here, and this is how you would find A transpose. The first row of A has become the first column of A transpose. The second row of A has become the second column of A transpose. The third row of A has become the third column of A transpose. And so you have A transpose. So if we have two matrices A and B, they are suitable for multiplication, as in A multiplied by B, if the number of columns of A is equal to the number of rows of B. So A multiplied by B is only possible when the number of columns of A is equal to the number of rows of B. Now see this example here. A here is of the order 2 by 3, so 2 rows and 3 columns. And B here is of the order 3 by 3, so 3 rows and 3 columns. The number of columns of A is equal to the number of rows of B. So A multiplied by B is indeed feasible. Now let's see how the multiplication actually happens. So let's take a look at a simpler example first. Let's say matrix A here is 1 and 2. Let's say matrix B here is 3. So we want to find A multiplied by B. So first let's see if they are suitable for multiplication. Matrix A is of the order 1 by 2. Matrix B is of the order 2 by 1. So matrix A has 2 columns and matrix B has 2 rows. So the number of columns of A is equal to the number of rows of B. So A and B are suitable for multiplication. Now, to actually multiply A and B, what you'll simply do is multiply the rows of A into the columns of B. That's really about it. So you'll multiply 1 and 1, and you add it with 2 multiplied by 3. And the resultant matrix will be 1 plus 6, which is this here. Now, a very handy way of a trick of finding the to confirm the order of the resultant matrix. So 7 here is of the order 1 by 1. To actually see if this is actually the correct order, you'll just simply find these two numbers. The resultant matrix must have the number of rows of the first matrix, which is A here, and the number of columns of the second matrix, which is B here. So 1 by 1. Let's see a more advanced example. Let's find A multiplied by B. First, let's see if they are suitable for multiplication. So A here is of the order 2 by 2. B here is also of the order 2 by 2. So the number of columns of A is equal to the number of rows of B. So they're indeed suitable for multiplication. And the resultant matrix will be of the order 2 by 2 because it will have the number of rows of A and the number of columns of B. Let's just see. See here, this matrix is of the order 2 by 2. Now, how did we find this? Simple. You'll first multiply the first row of A into the first column of B. So 2 multiplied by 1 plus 3 multiplied by 6. Now the second element, simple. You'll first multiply the same first row of A into the second column of B. So 2 multiplied by 7 plus 3 multiplied by 4. Now this is getting a bit messy here. Let's erase these lines. Now the third element of the resultant matrix, that will be found by multiplying the second row of A and the first column of B. So 1 multiplied by 1 plus 5 multiplied by 6. Now the last element, of course, will be found by multiplying the second row of A and the second column of B. So 1 multiplied by 7 plus 5 multiplied by 4. This is the answer of A multiplied by B. Determinant, adjoint, singular and non-singular matrices. So we'll be discussing the determinant of 2 by 2 matrices, singular and non-singular matrices, and the adjoint of A 2 by 2 matrix. So what is the determinant of a 2 by 2 matrix? Now the determinant of a 2 by 2 matrix, first of all, it is denoted by enclosing the square array between vertical bars instead of brackets. So see here, this matrix A, it is written down like this between two brackets. So the determinant of A is represented like this, two vertical bars instead of brackets. And then to find the value of the determinant of A, you will first multiply AD and then you will subtract multiply BC, and then you'll subtract BC from AD, like this here. So first enclose it in vertical bars and then AD minus BC. An example of this would be this here. Now see this matrix A. The determinant of A is found like, first you enclose it in vertical bars, and then you will multiply 2 and 3, and then you'll multiply minus 1 and 4, and then you'll subtract them like this here. 2, 3, minus 1 and 4, and subtraction. And you'll get this as the answer. That's all you need to know about the determinant of a 2 by 2 matrix. What are singular and non-singular matrices? So a square matrix A is singular if the determinant of A is equal to 0. Otherwise it is non-singular. So a square matrix A is singular if the determinant is 0, and if it's not 0, it's non-singular. That's about it. So an example would be, say, this matrix here. Now you'll have to find its determinant. So you'll enclose it in vertical bars, and then you'll find its determinant. You'll first multiply 1 and 8 and minus 4 into 2, like this here. And the answer is 0. So this is a singular matrix. What is the adjoint of a 2 by 2 matrix? Now, the adjoint of matrix A, like this, is denoted by ADJA, and that means the adjoint of A, and it is defined like this. Adjoint of A is equal to, now you'll see that what we've done here is we've switched A and D, and we've changed the signs of B and C. So the diagonal entries here, A and D and B and C, the first entry and the last entry will be switched, and the remaining entries, their signs will be reversed. Like C here, D comes here, A comes here, minus B and minus C. Now see this example here. To find the adjoint of A here, you'll switch 7 and 2, and you'll reverse the signs of 4 and 5. So this becomes this. So what is the inverse of a 2 by 2 matrix? So if you have matrix A, and if it is non-singular, and if it is a square matrix, so for the two conditions for the inverse of A to exist is that it must be non-singular, which means that its determinant, the determinant of A must not be equal to 0, and then it must be a square matrix, so basically an n by n matrix. The number of rows and the number of columns must be equal. If that is the case, then there exists an n by n matrix called A inverse. And it will also, the A inverse will also satisfy this particular property here. What this means is that the original matrix A multiplied by A inverse, or A inverse into the original matrix A, is equal to the identity matrix. And this is a 2 by 2 identity matrix. So if you multiply a 2 by 2 original matrix with its inverse, or the inverse multiplied with the original matrix, then it will give this 2 by 2 identity matrix. So the inverse of a matrix is found through this formula. The inverse of A is equal to the adjoint of A divided by the determinant of A. So to find A inverse, if A is this matrix here, so how will we find it? Simple. First off, you write down the formula so that you know what you're dealing with. And the second step is that you find the determinant of A. So the determinant of A is found like this. You multiply 5 and 1, and then you multiply 3 with 1, and then you subtract them like this. by 1, 3, 1, and then subtract them. And so 2 is the answer here. And then you will have to find the adjoint. So the adjoint of A is found like this. Now, the original matrix was this. What we've done here is that we've switched 5 and 1, and we've changed the signs of 1 and 3, and you get this matrix here. So this is the adjoint of A. So to find the inverse of A, you'll divide the adjoint of A with the determinant of A. And how you do that is basically simple. You'll divide each and every entry of the adjoint of A with 2. So 1 divided by 2, minus 3 divided by 2, minus 1 divided by 2, and 5 divided by 2. And that is the inverse of A. Properties of matrix addition, scalar multiplication, and matrix multiplication. So we'll have uppercase A, B, and C, three matrices A, B, and C that are of the order n by n, so n number of rows and n number of columns. And we'll also have lowercase c and lowercase d as two scalars. So the following properties are true for these. Number one, the commutative property with regards to addition. Now it's simple. It just says that if A plus B is equal to B plus A, so if you add two matrices A plus B, it is equal to, when you add matrices, B plus A. Simple. Now associative property with regards to addition. Now remember, in maths, everything in brackets is solved first and everything else afterwards. So it says here that if you add A plus B first and then you add C into it, it is equal to as if you first add up B and C and then you add A into the resulting matrix. Both of these are equal. Now associative property of scalar multiplication. Now again, brackets first, everything else afterwards. So if you multiply scalars C and D and then you multiply the resulting scalar with the matrix A, it is equal to as if you multiply scalar D into matrix A and then you multiply C into the resulting matrix. Both of these are equal. Now, existence of additive identity. The additive identity is a null matrix. Now let's say first a 2 by 2 null matrix is this 0, 0, 0, 0. This is a 2 by 2 matrix and it is an additive identity for all 2 by 2 matrices. So if you add a matrix into its correspond into a null matrix of the same order, or if you add the null matrix into A, both of these will give you A as the result. So if you multiply any 2 by 2, if you add any 2 by 2 matrix into this 2 by 2 null matrix, or if you add this 2 by 2 null matrix into any 2 by 2 matrix, it will give you that same 2 by 2 matrix as the result. So the existence of a multiplicative identity. An identity matrix is the multiplicative identities. For example, let's just rub this here. Now, see, it says here that the existence of a multiplicative identity, if you have the multiplicative identity multiplied with A, or if you multiply A with the identity matrix, it will give you A as the result. So for example, we have a 2 by 2 identity matrix. And if you multiply that with, let's say, this here, it will give you the same matrix. And if you just reverse this, if you put this matrix here multiplied with this, so if you put that here and this here, it will give you the same result, which is this matrix. Now the distributive law, this distributive property with regards to scalar multiplication. Now this here, again, brackets first, it says here that if you add up a and b and then you multiply the scalar c into the resulting matrix, it will be the same as if you multiply c with a first, scalar c with matrix a first, and then you add that into the resulting matrix of scalar c multiplied with matrix b. Both of these sides will be equal. And this is the second distributive property. If you add up the two scalars first and then you multiply the resulting scalar with a, it is equal to as if you multiply scalar c with matrix a and then you add that into d, scalar d multiplied with a. Both of these sides will be equal. Now 7, associative property with regards to multiplication. First, you will always solve the bracket. So matrix B, this says that matrix B into matrix C, the resulting matrix multiplied with A will be equal to as if you multiply matrix A and B and then you multiply the resulting matrix into C. Both of these sides will be equal. Now the left distributive property, it says that matrix B plus C, and if you add up matrix B and C and multiply the resulting matrix with A, it will be equal to as if you multiply matrix A with matrix B and then you add that into the product of matrix A and matrix C. Both of these sides will be equal. And 9, we have the right distributive property. The right distributive property says that if you add up A and B and then you multiply the resulting matrix with C, it will be equal to as if you multiply matrix A and matrix C and then you multiply matrix B and matrix C and then you add them up. Both of these sides will be equal. And the last property here is this one. It says that if you multiply matrix C into the product of matrix A and B, so first the product of matrix A and B and then you multiply scalar C into it, it will be equal to as if you multiply scalar C with matrix A first and then you multiply the resulting matrix with B, or if you multiply matrix C and matrix B and then you multiply the resulting matrix with A. All three of these will be equal. So solving system of linear equations by matrices. So we have these two simultaneous linear equations and we must find their solutions to the values of x1 and x2 through matrices. So what you'll do here is you'll write the constants of the left hand side on this matrix here and you'll write the variables in this column matrix. So variables will always be written in column matrices and you'll write the solutions in this matrix. So let's see the first equation. 4x1 plus 3x2 is equal to 5. Now look at this. Since we are doing rows into columns, so this will basically become rows into columns and that will give you 5 here. So 4 into x1 plus 3 x2 is equal to 5, and that is exactly this first equation. Now if you look at the second equation, 3x1 minus x2 is equal to 7. So 3x1 minus, so basically this becomes minus 1 since minus 1 into x2 is minus x2. So minus 3x1 minus x2 is equal to 7. And so this is the matrix form of these two simultaneous linear equations. And you can solve this for more variables or more equations. If you had another equation with these two variables, you'll just add the constants here. You'll just put two more constants here and one more solution. This will be solvable. If you had one more variable and if you had like another constant, so you'll just add one more column here and you'll add another row here. Simple. So this is now A, this is X, and this is B. So AX is equal to B and X is equal to A inverse B. So we have to find this A inverse. A inverse is basically the adjoint of A divided by the determinant of A. The determinant of A is simply 4 into minus 1 minus 3 into 3, which is this minus 13. And this is the adjoint of A. You'll basically switch the positions of 4 and minus 1, and then you'll invert the signs of 3 and 3. And A inverse is basically now this. And now if you put this into the equation of x is equal to A inverse B, x is equal to this here. So you'll basically, this is A inverse and this is B. Now what you'll do here is you'll first multiply the adjoint of A with B to get this, and now you'll multiply this determinant of A, and then you'll get this, which gives us the solution that x1 is equal to 2 and x2 is equal to 1. So we've solved the system of linear equations by matrices. So let's find the determinants of square matrices that are of the order equal to or greater than 3. And basically this is, for example, a square matrix of the order 4 by 4. Its determinant will be written down like this. You'll replace the brackets with vertical bars. So to find the determinant of a square matrix that has an order equal to or greater than 3, you must be familiar with these two concepts, the minor of an element and the cofactor of an element. So let's see what the minor of an element is first. The minor of an element, Aij, so basically the element in the ith row and jth column, its minor will be denoted by this uppercase M, Ij. And it is found by the determinant of the matrix formed after deleting the ith row and the jth column of A. So what that really means is, see this matrix here. This is a 3 by 3 matrix, and these are its elements. So basically the matrix obtained by deleting the first row and the second column of A is this matrix here. So see this. This is basically the elements obtained after deleting the first row and the second column. And if you just find the determinant of this matrix, it will give you M12. It will basically give you the minor of this element, A12. The minor of A12 is basically, this should be in vertical bars. The minor of A12 is basically this. So let's see what the cofactor of an element is. The cofactor of an element Aij is denoted by capital A, Ij. And it is defined like this. So basically you'll multiply the minor of that element into -1 raised to the power the row number and the column number. So basically what you'll do here is for example, to find the cofactor of the element in the first row and the second column, so basically A12, you will do -1 raised to the power row number which is 1 plus column number which is 2. So -1 raised to the power 1 plus 2 into the minor of the element in the first row and the second column, M12. So basically -1 raised to the power 3 into the determinant of this matrix. So you'll get this. And that is the cofactor of the element in the first row and the second column. Now to find the determinant of a square matrix of the order n greater than or equal to 3, you'll use both concepts. So if we have this matrix A here, and we will have to find its determinant, what we'll simply do is enclose A in vertical bars and basically just do this here. This is the formula for the determinant of the matrix. Now what you'll do here is you'll take the first element A11 and you'll multiply A11 with its cofactor. Then you'll add that into A12 multiplied with its cofactor. You'll add that into A13 multiplied with its cofactor. And you'll get basically this. Now, what you'll do is you'll put the values of M11, M12, and M13 that we will obtain. And this is basically what you'll get. A11, this is basically the minor of A11. And this is the minor of A12, and this is the minor of A13. And after doing all of the calculations here, you'll get the determinant of matrix A. And that's about it. Now the adjoint of a square matrix of orders greater than or equal to 3. Now if I have this matrix A here, then the matrix of the cofactors of A is this. So basically this is the cofactor of, wait a second, this is the cofactor of this. Now if you remember how we find this, let me just recap how we find the cofactor of an element. So the cofactor of A11 here would be -1. So basically A11 is equal to -1 raised to the power 1, the row number, and 1, the column number. And then you'll multiply that with the minor of A11. So how do we find the minor of A11? Well, you'll first delete its row and then you delete its column. And these remaining elements, the determinant of these remaining elements will be the minor. So A22 into A33 minus A23 into A32. This is basically the minor of element A11. And this is how basically you find the cofactor of A11. So you'll find the cofactor of each and every element in this matrix. And then what you'll do is you'll take its transpose. The transpose of this matrix here will become the adjoint of A. That's it. So, in other words, you'll take the cofactors of each and every element and you'll put them in a matrix form, and then you'll take its transpose to get the adjoint. Now, the inverse of a square matrix of order n is equal to or greater than 3 if A is a non-singular square matrix, so basically what non-singular is, if you remember, a non-singular square matrix is a matrix that has a non-zero determinant. And then if it is A is a non-singular square matrix of the order n, then there exists a matrix B such that when you multiply A with B or B with A, it will give you the identity matrix of the order n. So it will basically have the same order. And B is basically the multiplicative inverse of A, and it is denoted by A inverse. So what B is basically, if you multiply A with its inverse, it will give you the identity matrix, or if you multiply the inverse of A with A, it will give you the identity matrix as well. So that's one way to deal with inverses. Now, the other way is, if A is a non-singular square matrix, then what you simply do is you will divide the adjoint of A with the determinant of A, and that's about it really. So properties of determinants. Let's see, the first property is that for a square matrix, the determinant of the square matrix is equal to the determinants of its transpose. So if you interchange the rows and columns of A and take its determinant, it will be equal to as if you take the determinant of A itself. The second property is that there is a square matrix A and two rows and two columns are interchanged, then the determinant of the resulting matrix is equal to minus the determinant of A. So if you just switch two rows and two columns, if you interchange them, the net the impact on the determinant will be that its magnitude will remain the same, but its sign will change. And if there is a square matrix A that has two identical rows and two identical columns, then the determinant is equal to 0. So if you have a matrix that has two identical rows, or if it has two identical columns, then the determinant of A will be equal to 0. Similarly, if all the entries of a row or a column of a square matrix are 0, then the determinant of A is equal to 0. So, for example, in property 3, it will be something like if you had a matrix that basically it's the determinant of this matrix will be 0 as it has two identical rows, this row 1, two identical columns, column 1 and column 2. Similarly, in number 4, if the entries, let's say the determinant of this here, this will also be equal to 0 as this, as row 1 has all zeros. Now, if the entries of a row or a column in a square matrix are multiplied by a number, then the determinant of the resulting matrix is equal to Ka. Now this is very important. Let me explain how this works. Let's say if you had a matrix A, and let's say that this is matrix A, its determinant will be equal to, so determinant of A is equal to 2 into 1 minus 1 into 3, which is equal to minus 1. Now, let's just say that you multiplied, let's say B here is basically as if you multiplied uh, K, a constant K, a scalar K, with this, and if you multiplied k with this. So if you multiplied k with the first row and then you let the second row remain as it is, what will happen? Well, the determinant of, wait a second, the determinant of b is equal to k to 1 minus k 3, sorry, minus k 1 3. Now what has happened here? Well, as you can see, b can be written down as k into 2 1 minus. So what this says is this is equal to the determinant of a. So this is equal to k a. So what this basically proves is that if you multiply a constant k with the row, with any row of a, it will basically be multiplied, the constant will be multiplied with the determinant of a. If you multiply the second row of b with the constant k, it will give you the same result. If you multiplied the constant k with the any column of a, it would give the same result. So that is what basically property number 5 says. Now property number 6, if each entry of a row or a column of a square matrix consists of two terms, then its determinant can be written down as a sum of determinants. So if you had this, basically, this can be written down like this. You can write this down like this. Simple. And if to each entry of a row or a column of a square matrix A is added a non-zero multiple of the corresponding entry of another row, then the determinant of the resulting matrix is equal to A. As simple as that. And if a matrix is in triangular form, then the value of its determinant is the product of its entries on its main diagonal. So if you have a triangular matrix, then basically the determinant is equal to as if you multiply the entries on its main diagonal. So you don't really have to compute the entire procedure of the determinant. Just multiply the values of the main diagonal and you'll get the determinant of the matrix. So let's discuss upper triangular matrices and lower triangular matrices. So what is an upper triangular matrix? Basically, I will have to forgive me, my throat is a bit sore, but we'll make do. The upper triangular matrix is basically a square matrix, and if all the elements below the principal diagonal are 0, then it is an upper triangular matrix. Now, basically what this means is that every element that is in basically in a row number greater than the column number, it must be 0 for a matrix to be an upper triangular matrix. And for the lower triangular matrix, it's basically the opposite. It says that the elements, all the elements above the principal diagonal are 0. For the upper triangular matrix, it said that all the elements below the principal diagonal must be 0. And as it says in the lower triangular matrix, it says that every element above the principal diagonal must be 0. So basically, elements that are in column numbers greater than row numbers must be 0. So let's see examples. For an upper triangular matrix, let's just say a 3 by 3 upper triangular matrix. A, B, C,
D, E, F. Now you can see here that these three zeros, basically what A is, this is basically A11, this is basically in position A12, this is in position A13. So in all these cases, the column number is not less than the row number. And these zeros, the three zeros, this is in A21, this is A31, and this is in A32. Now, if you remember, it said that the elements must be 0 for all I is greater than j. Over here, the I is 2, j is 1. So this is 0. Over here, I is 3, j is 1. So this is also fine. This is I is 3 and j is 2. So also fine. So this is an upper triangular matrix. Similarly, if we take another 3 by 3 matrix and let's just do something different this time. Let's just say A, B, C, and D, E, and F. 0, 0. So this is the lower triangle, and see these zeros, this is in a 1 2, this is in a 1 3, and this 0 is in a 2 3. So what was the requirement for a lower triangular matrix? It said that for elements must be 0 for all I is less than j. See, I is 1, j is 2, I is 1, j is 3, I is 2, j is 3. So this is a lower triangular matrix. And we must remember something. The requirement for a triangular matrix is that we must look at the zeros. We do not really care what is inside the triangle. We really just care that the zeros are in correct places. So yeah, that's it. Now, symmetric and skew-symmetric matrices. So let's first discuss what a symmetric matrix is. If we have a square matrix A, and it is basically, the square matrix A is symmetric if the transpose of A is equal to A. So if you take the transpose of matrix square matrix A, it will remain the same. So see these examples. Now see this matrix here. If you take its transpose, so basically change this row into a column and change the second row into a column as well, you can see that it is basically the same. There is no change. So this is a symmetric matrix. Now there is another way to determine if a matrix is symmetric or not. You just outline the principal diagonal. Elements in the principal diagonal we are not concerned with, because if you take the transpose of a matrix, the elements in the principal diagonal will remain in the same positions. But the elements outside of the principal diagonal, basically this element and this element must be the same, this element and this element must be the same, this element and this element must be the same for it. So you can see a pattern here basically. So recognize this pattern and see this matrix here. This is a 4 by 4 symmetric matrix. How? See this? This is the principal diagonal. Now, basically, you will ignore the principal diagonal. This element and this element, they're the same. This element and this element are the same. These two elements and these two elements, you can see that they're basically somewhat like if you use a principal diagonal as a mirror. So you'll use the principal diagonal as a mirror, and on either side, they must be the same. Now you see this and this, they're the same. -2 and -2 here, they're the same. So basically what you must remember is either you can take the transpose, and if the transpose is the same, it is a symmetric matrix, or you can just use a shortcut. You encircle the principal diagonal and use the principal diagonal as a mirror, and the images on either side of the principal diagonal must be the same, basically as you can see in the mirror, and it will be a symmetric matrix. Now, what is a skew-symmetric matrix? If you take a square matrix A, it is called skew-symmetric if the transpose of A is equal to -A. So see this matrix B here. Now, if you take its transpose, it basically becomes this. And then if you take -1 common from this B transpose, what it does is basically this is matrix B, the original matrix B. And so this is a skew-symmetric matrix. Now, Hermitian and skew-Hermitian matrices. So a Hermitian matrix is let's just take a square matrix A with complex entries. Now, basically, a complex number is in the form A plus IB. Now, A is the real component of the complex number, and IB is the complex part of the complex number. The imaginary, not the complex, the imaginary part of the complex number. Now, it is the square matrix A with complex entries is called Hermitian if the transpose of the conjugate of A is equal to A. Basically, the conjugate of A plus IB, if we had A plus IB, if this is the conjugate of A plus IB will be equal to A minus IB. So let's just see this matrix A here. Now it has two real numbers over here in the principal diagonal, and it has two complex entries. So basically, the conjugate of A, the real entries will remain real entries, will not change them, but the complex entries will take their conjugate. So basically, 1 minus I becomes 1 plus I, and 1 plus I becomes 1 minus I. So if you take the transpose of A conjugate, it will give you, again, it will give you A. So this is a this is a Hermitian matrix. Now, Hermitian and skew-Hermitian, we'll talk about skew-Hermitian matrices. A square matrix A, we have a square matrix A with complex entries again, and it is called skew-Hermitian if the transpose of A conjugate is equal to minus A. So, for example, look at this matrix here. Now, the conjugate of this, the zeros will remain zeros, and these complex entries 2 minus 3i will become 2 plus 3i, minus 2 minus 3i will become minus 2 plus 3i. So basically, in the conjugate, you'll just change the sign of the imaginary part of the complex number. Now, if you take the transpose of this, it will become this matrix, which is equal to, if you take minus 1 as common outside, it becomes minus 1 into the original matrix A. This is matrix A. So this is equal to minus A. Thus, A is skew Hermitian. Now, let's discuss what the leading entry of a row is. Now, in any non-zero row of a matrix, the first non-zero entry is called the leading entry of that row. It is the leading entry. So, what this basically means is that the zeros before the leading entry of that row are named as the leading zero entries of that row. So what this basically means is that if you have, for example, let's say a matrix here, and let's say that that matrix is, say this matrix here, say this matrix here. Now, this is a non-zero row. Now, the first non-zero entry, which is this 2 here, is the leading entry. This is the leading entry. And the zeros before the leading entry of a row are named as the leading zeros, the leading zero entries of that row. So this zero here is the leading zero entry of this row. Sorry, leading zero entry. Now, in the second row here, this 1 is the leading entry and these two zeros are the leading zero entries. Now, what is the echelon form of a matrix? So let's have a matrix A, which is of the order m cross n, and it is in row echelon form if the first condition is if each successive non-zero row, the number of zeros before the leading entry is greater than the number of such zeros in the preceding row. Which this really means is, like, take this matrix here again. The number of leading zero entries in the second row is greater than the number of leading zeros in the first entry, and similarly in the third row, the number of leading zeros is greater than that in the second row. So this is the first requirement of the row echelon form, that the number of leading zero entries in each successive row must be greater than the one preceding it. Now, the second and third conditions of the row echelon form is that every non-zero row in A precedes every zero row. What this really means is that the non-zero rows in a matrix must always come before the zero row. The zero row, the row that has all zeros in it, must come at the end of the matrix. And the third condition for the row echelon form is that the first non-zero entry or the leading entry, as we have discussed earlier, like in this here, this number 2 here is the leading entry of this row. The first non-zero entry in each row is 1. That is the third condition for the row echelon form. Now, see this example here. Now, you can see that the very first condition of the row echelon form was that each successive non-zero row, the number of leading zeros must be greater in each successive row. Now, see here. There is one non-zero, there is one leading zero entry here, there are two leading zero entries, and there are four leading zero entries here. So that is the first condition fulfilled. Now, in every non-zero row, in A precedes every zero row. The non-zero row is this last row here, and since it is in the end, this is the second condition fulfilled, and the last condition is that the first non-zero entry in each row is 1. This is the leading entry of this row, and it is 1, and this is the leading entry in this row, and it is 1 as well. And this is just a zero row, so we do not consider it. Hence, this is in row echelon form. See this example here. These are, you can see that the leading entry here is 1. So, and the leading entry here is 1 as well. So the second condition is fulfilled. The third condition here is that the third condition here is fulfilled. The second condition is that the zero row must be at the end, and that is indeed the case here as well. But remember the first condition. The first condition said that the number of leading zeros in a row must be greater as the number of rows progresses. But as you can see here, there are 2 leading zero entries in the first row and 1 leading zero entry in the second row. So the first condition is the first condition is not fulfilled. Hence, it is a in non-echelon form. So, if you interchange the second row and the first row in this example, then it will be in echelon form. So, reduced echelon form of a matrix and the rank of a matrix. So let's discuss what the reduced echelon form of a matrix is first. So basically, what we have here, if we have a matrix A, it must fulfill 2 conditions for it to be in reduced echelon form. One, that it must be in its row echelon form for one thing, and we've discussed how what the echelon form of matrix is earlier. And the second condition is that the first non-zero entry in Ri lies in Cj, then all the other entries of Cj are 0. So what this confusing bit of words here means in simple terms is that the first non-zero entry, so basically the leading entry of a row must also be the only non-zero entry in its respective column. That's it. So let me explain this with an example. Look at this matrix here. How will we know if it is in reduced echelon form? So first we must confirm if it is in its row echelon form. So there are 3 conditions it must fulfill. Number 1, that the number of leading zero entries must be increasing as the number of rows increases, and that is indeed the case here. 1 0 in the first row, 2 zeros in the second row, and 4 zeros in the third row. The second condition is that the leading entries of the non-zero rows must be 1, and that is indeed the case here. This is 1 and this is 1. The last condition is that the zero row, so the row with all zeros, must be at the end, and that is indeed the case here as well. So this is in row echelon form for one thing. And the second condition is that the confusing bit here. So this one here is the leading entry in row number 1, and it is the only non-zero entry in its respective column. The second one, the one here, is the leading entry in the second row, and it is the only non-zero entry in its respective column. So this is indeed in reduced row echelon form. I re-emphasize, it is in reduced echelon form. So let's discuss the rank of a matrix. So this is a very simple concept. To see the rank of a matrix, you must first reduce it to its reduced echelon form, and then you just count the number of non-zero rows. The number of non-zero rows, which is R, is the row rank of the matrix. That's it. So homogeneous and non-homogeneous linear equations. Basically, a non-homogeneous linear equation, an equation of the form ax plus by is equal to k, a very simple equation. It is non-homogeneous if a is not equal to 0, b is not equal to 0, and k is not equal to 0. And for a homogeneous linear equation, you have the same equation ax plus by is equal to k, and a is not equal to 0, b is not equal to 0, but k is equal to 0. So that is the difference between a non-homogeneous and a homogeneous linear equation. Now, a system of homogeneous and non-homogeneous linear equations. So a system of non-homogeneous linear equations, you have a1x plus b1y is equal to k1, a2x plus b2y is equal to k2. These are two linear equations, and they are a system of non-homogeneous linear equations if k1 and k2 are not 0. Now, a system of homogeneous linear equations, you have the same two linear equations, and they are a system of homogeneous linear equations if k1 and k2 are 0. So basically the values of k determine whether a system is homogeneous or non-homogeneous. Now, consistent and inconsistent system of linear equations. For a system of linear equations to be consistent, it must have either a unique solution or infinitely many solutions. So let me explain what a unique solution is first. So if you have, say, x plus y is equal to 2 and x minus y is equal to 1. If you solve this, you get 2x is equal to 3, x is equal to 3 by 2. And when you plug that into any one of these equations, you'll have the same value. You'll get a unique value for x. So let's put it in equation number 2 here. You'll get a unique value for y. So let's put it in equation number 2 here. You get 3 over 2 minus y is equal to 1. Y is equal to 3 over 2 minus 1. So y is equal to 3 minus 2 over 2, which is equal to 1 by 2. So you get two unique values. You get 1 over 2 for y and 3 over 2 for x. So these are unique solutions. Now let me explain what infinitely many solutions is. So for infinitely many solutions, basically, let's just say you have this equation here and this equation here. When you simplify this equation, it becomes equal to this equation. As you take 2 common and 2 common here, and then you divide it by 2 over here, and you get x plus y is equal to 1 here as well. So both of these equations are equal, and so basically you will not have a unique solution for x and y. You cannot solve them. So they'll have, since they are both equal and lie on the same, they're both lie on the same line on a plane, they'll have infinitely many solutions as they intersect on infinitely many points. So for consistent system of linear equations, basically you either have a unique solution or you have infinitely many solutions. So that's that. Now let's discuss inconsistent system of linear equations. For an inconsistent system of linear equations, you need your system should have no solution. What that basically means is, let's just say you have this here, and let's just say you have this here. Now, quite clearly, these both equations contradict each other, as x plus y here is equal to 2, but x plus y here is equal to 1. So, you can clearly see that this will never have a solution, as they are contradicting each other. So, for an inconsistent system of linear equations, this is an inconsistent system of linear equations. Trivial and non-trivial solution of homogeneous linear equations. So remember, homogeneous linear equations are those in which the value of k is 0. So we have these system of linear equations, and first of all, the values of x1, x2, and x3, if you put the values as 0 in each one of these, they will give 0, and this will be a solution. And the solution 0, 0, 0 is the trivial solution. And another solution of the equations, other than the trivial solution, is called the non-trivial solution. As obviously, it is not necessary that the only 0, 0, 0, x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0 will give you 0 as the answer. No, you can have other solution as well, and that will be the non-trivial solution. So let's solve a system of linear equations by using a method called the Cramers rule. So we have the system of linear equations, and we'll convert it into a matrix form like this one here. And this column represents the variable x, the second column represents the variable y, and the third column represents the variable z. So first of all, you'll have to find the determinant of this matrix A. And you'll do that basically by multiplying these three elements of the first row with their respective cofactors. So you'll multiply 2 here with its cofactor. And you'll just for reminder's sake, how you'll find the cofactor is basically you'll first find the minor of 2 here. So you'll delete the row, you'll delete the column it's in, and you'll delete the row it's in, and then the remaining elements you'll take their determinant, and then you'll multiply -1, you'll uh, take the power of -1 to the row number and the column number of 2 here. So basically, the cofactor of this 2 here will be -1 raised to the power 1 plus 1, as it is in the first row and first column, and you'll take the determinant of, you'll multiply that with the determinant of -2, -2, 1, and -3, and then you'll multiply the 2 with this cofactor, and you'll get this basically, and then you'll add that into the same results for this 2 here and this 1 here, and then you'll get this entire equation. And you can refer back to the lecture where I discussed this earlier to clarify. And so by expanding this, by expanding this, you'll get this equation here, and when you solve this, you get the value of 27. So that is the determinant of A here. Now you have to find D1, D2, and D3 to find the values of x, y, and z. So what are these D1, D2, and D3? Well, you'll see that we've not really put these values, these constants here in the matrix. So what you'll do here is that in D1, you'll put the values, these constants, in place of the column x, and then you'll take its determinant. So 3, 1, and 2 will replace the column x, and the rest will remain the same, and then you'll take its determinant as you did before in the same manner, and then you'll get this 27. That is the value of D1. For D2, what you'll do here is you'll replace the y column with these same constants, and the rest will remain the same. And you'll get the value of 0. So D2 is equal to 0. For D3, you'll replace the Z column with the values of the constants, and you'll take its determinant, and then you'll get the value of 27. So you have D1, D2, and D3 now. Now, what you'll do here, to find the value of x, you'll do D1 divided by the determinant away. And what you'll do here, will you know that D1 divided by the determinant away is x? Because in D1, you replaced the x column with the constants. That is why you'll do x is equal to D1 divided by the determinant away. So you'll do 27 divided by 27 to get 1. For D2, for y, you'll do D2 divided by a, because in D2 you replace the column of y with the constants. And so you'll do 0 divided by 27 to get 0. And similarly for z, you'll do D3 divided by the determinant of a to get 27 divided by 27 to get z is equal to 1. So that's the Cramers rule. So let's solve the system of linear equations by using the inversion method. We've discussed the Cramers rule before. Now we'll discuss the inversion method. So we have the system of linear equations. Let me just turn the pen on. So we have the system of linear equations, and basically, first of all, you can write the third equation here as 0x plus yz minus z, 0x plus y minus z is equal to 1, as there really is no value for value for x. So now in matrix form, what this entire system will look like is basically this. As you know, it's rows into columns. So the first equation here can basically just be done by multiplying this first row with the variables column, and same is for the other two rows. They'll solve for the other linear equations here. Now you'll put this equal to this, as these are the constant values that the variables are equal to. Now you have these matrices. You'll give this matrix the name matrix A. The variable matrix will be called X, and the constant matrix will be called B. So the coefficient matrix A, the variable matrix X, and the constant matrix B. Now, what you'll do here is you have to find the values for X, Y, and Z. So you'll take A on the other side, and it becomes A inverse B. So to find the variables to solve the system of linear equations, you must find A inverse B, and you'll call that equation 1. Now, to find the determinant of A, again, you already know how to do this, but just for a recap, you'll basically just, for example, this here. What this is you'll basically multiply this 1 here with its cofactor, and then you'll add similarly -2 multiplied with its cofactor to get this, and then you'll add that with this 1 here multiplied with its cofactor to get this, and then by expanding this you'll get the value of determinant of A as -2. Now since A is not equal to 0, we can find A inverse. It is a non-singular matrix. So to find A inverse, you basically need two things. You need the determinant, but you also need the adjoint of A. So you can refer back to the video where I explained how to find the adjoint of A. Just for reference, you'll basically make a matrix of the cofactors of each and every element here. Each and every element, you'll find every element's cofactor, and you'll make a matrix of it. and then you'll take its transpose, that will be the adjoint away. So just for clarification, let's take the cofactor of element 1 here, a11. So minus 1 raised to the power the row number which is 1 and the column number which is 1 as well. And then you'll multiply that with the determinant of the minor of this one. So basically you'll delete this, the column it's in and the row it's in, and you'll take the determinant of the remaining elements. So this is how you find the cofactor, and that results in 1. So the cofactor of 1 here is 1. And you'll take the cofactor for each and every element in this matrix as such, in the same manner as you've done for the 1 here. And then you'll take the transpose of the resulting matrix. This is the resulting matrix, and you'll take its transpose to get the adjoint away. So the adjoint away is this matrix here. Now you'll divide the adjoint away with the determinant away, and you get this here. And then, as you remember, x is equal to A inverse. This is A inverse, and this is B. You'll solve this. Oops. My bad. So you'll solve, basically you multiply this matrix here with this matrix to get this matrix, and then you'll divide that by minus 2, and so you'll get this as the result. So x is equal to 1, y is equal to 1, and z is equal to 0. And that's how you'll solve this. So let's solve a system of equations by echelon and reduced echelon form. So we have the system of linear equations. We must convert it into its augmented matrix. So what you'll do in an augmented matrix, you'll separate, put a slight separation using these triple dots here. On the right hand side, you'll put the constants in column form, and over here you'll put the coefficients in their respective columns. So this is the x1 column, this is the x2 column, and this is the x3 column. The coefficients of x1, the coefficients of x2, and the coefficients of x3, and this is the constant column. And this is in its augmented matrix. And now basically you'll have to do row operations to convert this into its echelon form. We've discussed the requirements for a matrix to be in echelon form. So you must first have the leading zeros must increase as the number of rows increases. So there must be zeros here and here. So how will you do that? So basically you'll form row operations by subtracting 2r1 from r2. This, just to be clarified, this is r1, this is r2, this is r3. This entire row is r1, this entire row is r2, and this entire row is r3. So subtracting 2r1 from r2, you get this row. And then you subtract 5r1 from r3 to get this. And so now you have two zeros here instead of 2 and 5. So the next step now is you must have the leading entry in each row must be 1. So this 7 here should be a 1. So you'll convert this by doing another row operation. So you'll subtract r3 from r2 to get this matrix. Now, what you must do here is you must convert this 6 into a 0, as the number of leading zeros must increase. Since there's one zero leading zero in row 2, there must be 2 leading zeros in row 3. So what you'll do here is you'll perform another row operation you'll subtract 6R2 from R3 to get this. And now you must remember, as I mentioned earlier, the leading entry must be 1. So this 19 must become a 1. What you'll do here is you'll perform another row operation. You'll divide the entire row 3 by 19 to get this. Now this matrix is in its echelon form, not its reduced echelon form, it is in its echelon form. You can solve the system of linear equations just by using this here. And how you'll do that is you'll write them down, you'll write the rows down in their equation forms. So this row 1 becomes this equation, row 2 becomes this equation, and row 3 becomes this equation. So the value of x3 is explicitly 24 by 19, as we've seen from the echelon form. You'll put the value of x3 in this equation 2 here to find the value of x2, and by solving it, you get the value of x2 as minus 9 by 19. You'll use the value of x2 and x3 and you'll put them in equation 1. And when you put them in equation 1, you get the value of x1 as 11 by 19. So the x3 is 24 by 19, x2 is minus 9 by 19, and x3 is 24 by 19, x2 is minus 9 by 19, and x1 is 11 by 19. Now, let's solve this by turning the echelon form into its reduced echelon form. In a reduced echelon form, you must remember, as I've mentioned earlier before, is that the leading entry in each row must also be the only non-zero entry in its respective column. So this one here is clearly the only non-zero entry in its column. But this one here is not the only non-zero entry in its column. Minus 2 is also in its column. And and every element in the last column is a non-zero entry. So we must convert this. So what we'll do here is we'll perform another row operation. By adding R1 and 2R2, you get this matrix. So now you see this leading entry of the second row is the only non-zero entry in its respective column. Similarly, we'll perform these row operations to convert this matrix into this matrix. Now this leading entry 1 here in the third row is the only non-zero entry in its column. Now each leading entry is the only non-zero entry in its respective column, and this is the reduced echelon form. And simply you can see that x1 is equal to 11 by 9, x2 is minus 9 by 19, and x3 is 24 by 19, and so you've solved the equation.